Right, so we now introduce coordinate transformation. Right, so we consider a vector value function. Okay, so that it consists of two component functions called the v function and w function. Right? Right, it's on an open subset of the xt plane. Okay. So as I mentioned last Tuesday, that we would like to use the coordinate transformation to simplify our semi-linear PDE. Okay. And so we will use coordinate transformation, so now we defined it formally. So U are an open subset of the xt plane, and so it goes to the so-called VW plane, okay, because that it has two components renamed by U and W. All right, if this vector value function has the following property. And I list the three properties here. First of all, both v function and w function, okay, are continuously differentiable on U. Okay, first of all, which means that this one has two first-order partial derivatives, right? And these two first-order partial derivatives are continuous. Okay, and similarly, the two first-order partial derivatives of W are also continuous. Okay, so this is the definition of continuous differentiable. And the second, the vector function is 1-to-1 on U. Okay. And the third one, the Jacobian determinant J of VW. Okay, so this is V. Right, so the Jacobian determinant, which is the determinants of the Jacobian matrix. All right, so as we know, this is just right. So this Jacobian determinants, it's non-zero. Okay, for every point xt in U. Okay. Now so I make a remark. Since the Jacobian is continuous on U, is continuous. Either the Jacobian determinant is positive for all points in U, or Jacobian determinants is negative for all points in U. Okay? Why? Because if the Jacobian determinant has positive value and a negative value there, then by continuity it must have the zero value at some points in the open subset U. Okay, so this is because of continuity. But we say that the Jacobian determinant never zero. Okay, never zero. So this is impossible. So either the Jacobian determinants are positive for all points in U, or the Jacobian determinant is negative for all points in U. Okay, so you will have these three properties. So any vector function defined on U give us. Okay. So now I state a remark. Okay. A coordinate transformation okay, a coordinate transformation which an open subset of the xt plane So a coordinate transformation is an open mapping i.e. it's open mapping i.e. for any open subset V of U, the image, okay, the image here, X an open subset of R square. So it's called open mapping, right? So any open subset in the domain U, okay, give us the range here, that which is also an open subset. So in particular, the W defined to be VW of U. Okay, so the whole domain, okay, well, it's an open subset of the VW plane. So we call this one call as the VW plane. Okay, because we say VW, right? So we call that the VW plane there. Okay, so W, X, let me say it. Thus, VW, U from W is a one-to-one and onto mapping. Okay, so V to W is one-to-one onto. Yeah, open set. So it's called open mapping. Yep. Okay, and so coordinate transformation is just a special case of open mappings. They are open mappings which is not coordinate transformation. Okay, so coordinate transformation has sufficient property to guarantee that it is an open mapping. Okay. Now, so if we write the vector function VW from U to W to the range, right? Then this is become to one-to-one onto. So it has inverse mapping, right? So the inverse mapping okay? So the inverse mapping will be called ST, all right? Okay, the inverse mapping here, right? So we will call from W to U. Okay. The inverse mapping is also a coordinate transformation. Okay. Okay. So that the inverse mapping has the above three properties. Okay. So both the V and the X and T, are continuously differentiable, and the second is one-to-one, of course, on W. Okay, and the Jacobian determinants of this vector value function is also non-negative, always non-zero. Okay. In particular, we have that the Jacobian, right, of xt and VW, okay, times the Jacobian of xt. Okay. Yeah. Which one?
The third line. Is that opens on the
yeah. We call R2 here as the VW plane. Just like we call, because the U is in R2, right? And this R2 we call the XT plane. Okay. The same. R2, but this is our term. In this context, okay, you can say just R2 only, right? Okay. And the Jacobian here, the Jacobian is the inverse, the Jacobian of the inverse mapping here, okay, multiply times with the Jacobian of the original mapping. Okay, so this is, we know this is, all right, so this is Jacobian of the inverse mapping. Is equal to 1. And this can be done by chain rule, okay? So we have that, so the can have, okay. And this Jacobian, of course, can be expressed in terms of xt, right, by this substitution, so that I use another color. So this one can be rewritten here. So it's xt. Okay. So once we do the substitution of the coordinate transform, so this is become to a function of xt, and this is also a function of ft. Okay, and then this one becomes to okay. So the expression here, they are functions of x and t only. Okay. So this is for, so now for all xt in U. Okay. And by chain rule. Random application give us this one. Okay, so that's why that the Jacobian always non-zero, because this Jacobian times this Jacobian is equal to 1, so they're never 0. Otherwise, it cannot be equal to 1 for all points. Okay. Okay, so the inverse mapping of a coordinate transformation is also a coordinate transformation. Okay. And also it must be an open mapping too. Okay. Okay. Now alright, so now we want to apply, we want to find suitable coordinate transformation to simplify our semi-linear ODE. So we now make some assumption, assuming that the solution U of xt of the semi-linear PDE in 4.1, okay, is twice continuously differentiable. On an open subset U of the xt plane square. Okay, so our goal is to find twice continuously differentiable coordinate transformation VW on an open subset V of U. Okay. We may not be able to find a coordinate transformation on the whole open subset. Okay, because the open subset is the domain for the solution. Okay? Okay. So maybe it's too big to find coordinate transformation, but at least we can find coordinate locally. Okay, find a local transformation. All right, as the merit of the inverse function theorem we mentioned last Tuesday. Okay, because in last Tuesday we know if a vector function is from a subset of Rn has a non-zero Jacobian determinant at certain points, then in a neighborhood of that point we can find coordinate transformation. Okay. So that so our goal is to find a twice continuously differentiable coordinate transformation such that the semi-linear PDE in 4.1 can be reduced to a simpler standard form on V. Okay, so we would see that. Okay, so if such a coordinate transformation VW exists, on V, its inverse xt is also twice continuously differentiable. Coordinate transformation. On W, which is V. Okay, so we must have that. So we then that U tilde of VW, okay. Our solution U is in the xt plane, right? Now, when we do the coordinate transformation to the VW plane, we want to know in this new coordinate system what is the corresponding PDE. Okay. Before that, so we know the solution here, this function under the coordinate transformation. Okay, we call this is U tilde, and the U tilde is actually, so we use the inverse coordinate transform xt, right? So x and t coordinate can be obtained from the new coordinate VW coordinate. Okay. So that we have that for all points in W. Okay, in W. And this one, which is twice continuously differentiable. W. Since U is twice differentiable, and x and t are also twice continuously differentiable. Okay. And so that you can return back the original solution by U tilde and the Vxt. Again, the coordinate transformation. Okay? So this is the solution of all semi-linear PDE, okay, in the xt plane. But the U tilde is the new functions, okay, in the VW plane. All right, so by chain rule, so now we want to know that, so this U tilde must be the solution for the corresponding PDE, right, in the VW plane. Okay. All right, so we do. So this is quite similar, right, to what we have done when we use the numbered method to find the general solution of the one-dimensional wave equation last Tuesday. It's quite similar. So I will do that quickly. All right, I will do that quickly because the procedure is so standard. Okay, and the Ux is the UV plus X. Okay, and so UTT. So this is the first order positive derivative, and then the second order positive derivatives. Alright, so now I just write down. I will omit the detail, okay, of the derivation. Okay, I need. Let me see. T, yes. VW, T and VT, yes. U, V, VTT. Okay. Plus okay, so this is long. Okay, and UTX would be U plus X and VT plus UV VTX plus U and Vx plus U Wx and Wt plus Wtx. Okay, and then the last is Uxx, and Uxx is UVV and Vx plus U Wx and the Vx here plus U V tilde Vxx plus U tilde W Vx plus U W Wx and Wx here plus U W tilde Wxx. Okay. So this is the everything we have. Now by substitution, now the semi-linear PDE, okay, in checkpoint 4.1 on V, okay. On V, remember on V is in the XT plane, right? Become there. So we will see that A Vt square plus B Vt and Vx plus C Vx square and U Vv tilde Vv. Okay, so this is coefficients of the coefficients corresponding to this second order partial derivatives of U tilde and 2A Vt Wt plus B Vt Wx plus B Ux Wt plus 2C Vx and Wx and U tilde Vw. Okay. All right, and we know here by continuity these two mixed partial order differential partial derivative are equal. Okay, by continuity. Okay? Because we assume that U tilde they are we assume the solution U is twice continuous differentiable. and the coordinate transformation are also twice continuous differentiable. So U tilde is also twice continuously differentiable. Okay. Okay, and so they are equal. So we just combine them together to one term. Okay. Plus A dot T square plus B dot T dot X plus C dot X square and U dot W. Okay. Equal to F tilde of V W U tilde and U tilde V and U tilde W. Okay. Now on W here in the V W plane. And once again, you see that it is also a semilinear PDE. Okay, so in the xy plane we have the semilinear PDE. Now, after coordinate transformation, we have another semilinear PDE. Okay, on W. And W is just open set in the VW plane. All right, and you see here, the original ABC coefficients are functions of xt, but x is a function of VW. T is also a function of VW. So this one is a function of VW. Okay, so it's a function of VW. So only is a function of two independent variable VW here. Okay, and similarly, this coefficient is also a function of the two independent variables V and W, and also here the same. Okay, so this is a function of two independent variables V and W. Okay, so once again we have that. So we have an opportunity to simplify this PDE. Okay, we have that. And where F here. And UV and the UW, okay, can be obtained from A, B, C functions, okay, and the F function. And it's a little bit complicated, right? A long term. So please see the lecture notes. Okay. So I will not repeat it. You can do it at home, right? You can derive what is the F tilde. Okay. Right. So finally, the F tilde will be depend on the two new independent coordinates and the U tilde sub V, U tilde sub W. Okay, so you can obtain that, right? Right. So you can do that. Now, if if the semi-linear PDE, okay, is hyperbolic on V, okay? So suppose we find an open subset V of U, right? So maybe V is quite small, okay? So on that, so if the on V means that the V square xt minus 4ac, all right, is positive for all points in V. Okay, suppose, right? So suppose that the semi-linear OPD is locally hyperbolic. Okay, by our definition, right? So every point in this V that we have this inequality. Okay. Then the coefficient of U tilde VV and U tilde WW, so that there's two, this one and this one. Okay, the two can be made, right? Can be made identical, made identical to 0. Okay, on W. Okay, on W here. So i.e. maybe I use V prime. Okay, so now I use V prime for good correspondence. Okay, V prime. Good. On V prime. So that means that the A square of Vt plus V, Vt, Vx plus C square of Vx is equal to 0. So identical to 0, because this is a function of xt. Okay, as function of xt, and this is the 0 function. Okay, which means that if xt is in V, okay, then this is to be identical to 0. And also, we can make identical to 0. Okay, how? Well, it depends on the V and the W you select. So by rating Vt divided by Vx equal to, so you can solve, because this is the, you can think about that, this is the, for here, it's a quadratic function of Vt and the Vx. And so you do the ratio here. You can see that this is minus b plus square root of b squared for ac and 2a. And because you can see that this is basically the same quadratic equations, right? The same, because they have the same coefficients there. Okay. So you have Wt, Wx is equal to minus B square minus 4AC and 2A. Okay. Okay, so they are real functions. This is guaranteed by this inequality. Alright, so you see that if we have a coordinate transformation, because these are necessary conditions, right? As we see, say, if we have if such a coordinate transformation exists, so if it exists, then we have these necessary conditions. Okay. All right. So to simplify, we are able to simplify them because we can let these two coefficients to 0, right? And so that the V and the W should satisfy these equations. Any questions up to now? Okay, and where, because we put A in the denominator, so where we assume that AXT is not 0 for all points in V. Okay? Now, since ABC are continuously differentiable on V, that V and W can be made twice continuously differentiable on V. Okay, and so we will write down so this is we'll write down to be this equation, I will call it 12.4.2, okay, for reference, and 12.4.3, okay, all right, on V. And we can make that because BAC, okay, we will assume that they are continuous differentiable, as we usually assume for the for our semi-linear PDE. Okay. Okay, and so they are continuous differentiable. Okay, and so that we can make U and the W to be twice continuous differentiable on V. Okay, by from 12.3.4.3, okay, from this relationship. Okay, and also, since Vx and Wx are non-zero for all points in V from here. Okay, because when we write down this way, so we also assume that Vx and the Wx must be non-zero. Okay. So the Jacobian determinants. Okay. So now we see VW xt. All right. And as we know, this is the Vx Wt minus Vt Wx. Okay, so we have Vx, Wx, and Wt, Wx minus Vt, and Vx here. Okay, so this is the Jacobian determinants. Okay, as we know that, and we move out the factor Vx and Wx here. So this is become to the ratio here. And when you look at the ratio, so this is minus Vx, Wx. So this one minus this one give us A and the square root of B squared minus 4AC here. Okay? And you can see that this is not zero. Okay, for all points in V, because this is non-zero, this is non-zero, this one is positive, and A is non-zero. So you can see that this product is non-zero, right, for every point in V. So now we can see the Jacobian is that. Okay, and the mapping, so the coordinate transformation we have, okay. So the Jacobian determines non-zero, and the V and the W here is not only continuous differential, but also twice continuous differentiable. So it's much more stronger, right? So we have made them twice continuous differentiable V and W. Okay. Okay, and so the only requirement is here is that we need that the mapping should be 1-to-1, right? So we need a 1-to-1 mapping here. We need a 1-to-1 mapping. Okay. The first one and the third one has been satisfied. Okay, but we are questionable for the second property. Okay, so it's questionable. Okay. Now by the inverse fountain theorem, this vector valued function VW is 1-to-1 locally at every point in W V. Right, because again, the Jacobian is non-zero. All right, so we can find a neighborhood for every point in V. We can find a neighborhood, all right, such that the vector value function, which is 1-to-1. Okay. All right, so without loss of generality, okay, so we may assume that V and W is 1-to-1 on V. Okay, so now we can think about V is truly local, okay? It's really local, right? Okay, so in V, with V properly chosen, so that VW is indeed twice continuously differentiable coordinate transform. On V. Right? So, which means that we are successful. We really find a coordinate transform already. Okay? Because originally we just attempted to find one of them, right? So we want to find, so remember, in here, if such a coordinate transform, so we try to find necessary conditions. And from the necessary conditions, we justify that, yes, there exists a coordinate transformation. Such that we can simplify the original semilinear PDE. By what? By letting these two coefficients to be 0. If the PDE of the original semilinear PDE is hyperbolic, okay, hyperbolic in an open subset, right? So of U, and from this we find the relationship between the coordinate transformation V and the W here. So these two equations specify the some specific property of our legitimate coordinate transformation. And in here, we assume that V and V sub x and W sub x are non-zero. Okay, just as we assume A is non-zero. Okay, for all points in the open subset V. Right. And from this calculation, we find we really have non-zero Jacobian. Yes? What?
Why is that always known? How do we make sure that the probability hardware will not pass through 0 at any x?
You mean these two first order partial derivative? Or this one?
Why is that?
Because that assume, I have to say, when we write down this ratio, we assume that they are, say, Here we assume non-zero, or maybe I will write down non-zero. Okay. But actually, we can make it non-zero. Well, when we try to solve them, so later on we will solve because this is the differential equation, right? Okay, so they are differential equations. Actually, they are first order partial differential equations. Right, and we will try to make it so by making so maybe I rephrase a little bit. So by making Vx and Wx non-zero, right?
So that line should be added to the assumptions from 1, 2, 3, and 4.
Yeah. But okay. But if now here. No, this one just says that the Jacobian determinant is non-zero at the point, which.
I mean, if you want to assume certain values right in, maybe at behind point 1,
But they are just required to be continuous differentiable, not necessary to be both zeros.
we are now discussing the case that there are
Not yet, because okay, up to here, okay, up to here, they are just necessary conditions. So if we do have V and W, we have a coordinate transformation. Then we have we do this one, all right. And we want this coordinate transformation to make these two coefficients to be zeros. Why can we do that? Because it's we assume that it's hyperbolic on some open subset V of U. Okay, so that, and from these two requirements, we have the relationship. Now we build relationships about the first order partial derivative of V and W. Okay, and here, when we write here, we want to make the V and the W such that the Vx will be non-zero and Ws to be non-zero. Otherwise, we can't write down this one. Just like we assume A should be non-zero for all the points in V. Okay, so when we write down this way, we purposely want to have V and the W such that V sub x and V sub W sub x are both non-zero at every point in V. Okay, so this is our intention. Otherwise, we have no confidence to write down this requirement, this equation here. Okay, so I should say by making Vx and the Wx non-zero as required in 12.4.3, right? This is required when we write down this equation. All right. So later on, when we really construct the V and the W, we have to check that both of them should be non-zero. Okay. And by making this to be true, then we show that the Jacobian determinant must be non-zero too. Okay. And in that case, then the three properties of coordinate transformation, number 3, 1 and 3 are justified. But the second one is still questionable. Okay? But fortunately, when we use the inverse function theorem, we know that if a point has non-zero Jacobian determinants, then we have one-to-one mapping locally and onto. So that, but it is possible that we have to nail down, right, the V. We have to shrink the V so that it is in a neighborhood of a point in V. So we can arbitrarily select a point in V and find a neighborhood. All right, so that there is a one-to-one mapping for that. Okay. Okay. All right. Yeah, first order will be sufficient. But here we require second order twice continuously differentiable. This is much stronger.
I mean, the inverse function only says that if you are differentiable from left to right.
Yes.
First order, then you can say that it's differentiable from left to left.
Yes. Yeah.
And you assume that from left to right you have the second order continuous differentiable.
Yeah, stronger. So a twice continuous differentiable function implies it is continuous differentiable. Yeah.
But I mean, you now say that it implies that you have twice continuous differentiable ability from right to left.
No, but if the forward direction is twice continuous differentiable, then the inverse function must be twice continuous differentiable.
Yeah, but the inverse function theorem really says that.
Hmm?
Like, this is not from the inverse function theorem.
Yeah, that can be deduced from inverse function theorem. Well, the inverse function theorem tells us that we can build a function from some subset, the neighborhood. So maybe I use W, go to 2, right? So that this is one-to-one. Yeah, this is one-to-one. And so when we restrict to, so this is one-to-one and onto. Okay, it's onto there. Right. Now, if furthermore f is twice continuous differentiable, then the inverse function is also twice continuous differentiable. Huh? By chain rule again. Yeah, still by chain rule. So that it's the inverse function theorem just guarantee us we have inverse function. Okay, but once we have inverse function, then then when the original function f is twice continuous differentiable, then the interfunction is also twice continuous differentiable, just by chain rule. You do that again. Oh, okay. As we see, for example, you can use either way. You can use or you can use f inverse, fx is x. Right, so you do the G here. Suppose, okay, you have that. All right, so now when you do the partial derivative of x, right? And the partial derivative gives you, this is 1. But okay, I think I have to, okay, this is identity mapping, okay, so that we have f inverse. Okay, this is the vector function. Okay, the vector function. The vector function. So the Jacobian. Okay, the Jacobian matrix at VW, then the Jacobian matrix at XT, okay, VW is equal to, the Jacobian is identity 2 by 2. Is that okay? This is a chain rule, right? This is a chain rule about that. So you have the product with that. And the second order, it go to the similar way because it's a little bit tedious because you are multi-dimensional, so you have to make it's a little bit messy that. Okay. So this is the matrix, and now you will do, so now the vector function can you can do the differentiation again, right? Because now you have vector functions again.
Yeah, but that is also
What? Jacobian is a scalar function. So we have to deal with the matrix, so not Jacobian. Sorry about that. This is D. I'm sorry. The Jacobian matrix. Right? So the Jacobian matrix. So this is the inverse matrix of the Jacobian matrix of F. Because this is identity. This is the identity there. Okay? And then you have, so now you can do the differentiator, because this is finite dimensional. Okay, so once again, okay, I write here, F and inverse mapping. So F has F1, F2, and G is the inverse mapping. So we call the G1 and G2. Right? So now G1 of F1 xy and F2 xy is equal to x, right? And G2 F1 xy, F2 xy, and y. So this is the inverse mapping meaning, right? Okay, now the partial derivative. So this function is a function of xy, and so if we take the partial derivative of the whole thing, by chain rule, the partial derivative will be g1, say v, okay, and v is f1, so this is df1 and dx plus w, and which is equal to 1, and it's 0. It's 0. Okay, so we have 4 equations. Now so basically from these equations you can solve these 2 partial derivatives. Okay, you can solve. You have 2 equations. What?
Actually, F1 and 2.那它应该是 partial G1 partial F1.
No, but we use V to denote F1 of xy, W denotes
F1 of xy 不是 F1。
what?
F1 of xy 应该就是 F1，不是一样的。F1 本来就是一个 function。
Yeah, I know it's a function. So F1 is the component function. We rename it as V, and F2 R2, right? Okay. If you don't want this to be confused, maybe you will say, that's fine. F is V W. Okay, you can say that, and the function. Yeah, I know. So you get xt. Yeah, so these xt functions. Okay, and you can use v w. Yep, that's fine. Okay. Right? And maybe you use, if you like. So now you have x here, and so this is 0. So you have x and v xt and w xt if you like. This is become 2x. And then you will be confused by yourself, right? So that it's better to use the inverse mapping to be G1 and G2. Okay. What? Yeah, so G1 is okay, right? So G1 give you the x and the G2 give you the t. Give you t. Go back. This is the inverse mapping. So this is G1 here. And the G1. So you have so you can solve this then together. If you want the second derivative, then good. So if you take the second derivative once again, right? You have you will do that again. No, we need this one. Plus is equal to 1. Okay. Now, again, this is a function of xt. So we do the partial derivative again. So we take a partial derivative again, and so this is square, and the terms that square plus this is second order partial derivative we have, and we need this one, and this is continuous function again. Okay. Yep. And and we need this one. Okay, the equation, this is 0. Come to 0. Okay, and you can solve the second partial derivatives. Yeah, and so the existence, the similar way you can
This shows that if it exists, then it will be.
I know. So, but the existence, I mean, you can go through the details. Just like, if you have a question, you have to question why I can write down this one, right?
No, first order is fine.
Why? You have to prove the existence again. Otherwise, I cannot write down this one, right? This is when they exist, then I can run it.
The first order theorem says that the first order is fine. I mean, the first
Yeah, that has been proved in the inverse function theorem. But the same idea we can use to prove that if the coordinate function is twice differentiable, twice continuous differential, then its inverse is also twice differentiable. Yeah. You would need, you just go to the Ruding's textbook. This is they are standard proof for you. Okay. Yeah. Yeah. I'm sorry because okay. A simple example is that if it's not so complicated, if f is a function is only a single variable from u to w, and the g of x is w to u, all right, and gy. So f g x and f of g is y. Suppose that. Then from that we know the derivative is equal to, if I am not, is equal to the inverse, right? So the derivative gy that's g prime of f of x times f prime of x equal to 1. So which means that g prime of f of x is equal to 1 over f prime of x. And you may ask me why, if this is true, why I can write down this one? You need to prove that the existence of g prime, right? But this is guaranteed by the chain rule. The chain rule has proved it. When I say I apply chain rule, which means that this is a chain rule, and the proof of the chain rule shows that the g prime exists. Okay, the inverse function, if it's differentiable, then that is differentiable. Okay, and if we have the second derivatives, so you can apply so now if it to exist, then we have g double prime f of x f prime of x square plus g prime f of x and f prime of x f double prime, okay, is equal to 0, and so you can find which is equal to g prime f of x f double prime of x and f prime of x square if this one is non-zero. Okay, so you can have this one, and from that you can so this is a necessary condition. Okay, and then you can formulate the existence of the g double prime.
My only question is the existence.
I know. But the prefix is a standard procedure in calculus. Okay. All right. So many, yeah. I have to. All right. So we have established the local property. Okay. All right, now the two equations in 12.4.3, the two equations can be used to determine the v coordinate curves as well as the w coordinate curve as follows. Alright, so for the v coordinate curves, okay, so vxt is the constant. So we have, okay, by total differential, so dv is equal to v sub x and dx plus vt dt equal to 0. Right? So by taking the total differential, all right, so that's the first order ODE dx dt, because this is 0, right? So dx dt is equal to minus vt and vx here, right? And this is equal to 2a b minus square root of b squared minus 4ac. Okay, and this ODE governs the family of v coordinate curves. Okay. Right. So we so that because the coordinate curves, they must satisfy the equation like that, so that you have the coordinate curves. Okay, and from this total differential, you get the differential equations. Okay. Okay. And similarly, with the W coordinate curves the xt equal to constant. So we have the wx x dt dx plus the t dt equals 0. Okay. By taking again total differential, so that's the first order ODE dx dt and which is minus w sub t w sub x which is equal to b plus square root of b square minus 4ac 2a. Alright, so now this governs the family of double coordinate curve. So we have these two family of coordinates curves are called the characteristics of the semi-linear PDE on this open subset. And in this case, V and W are called the characteristic coordinate of the PDE on V. Right. So basically, the coordinate transformation we used is actually the characteristic coordinate transformation. Okay. Okay. Now, so while the coefficient of yield VV and U to the W made equal to 0, because we make them to be 0. Now let's look at the coefficient of the mixed second order partial derivative term. Okay. Right, in the characteristic coordinate. Okay. Now the coefficients of the mixed second order partial derivative term becomes, so we can so 2a Vt dot t plus b VT WT plus WX B Vx WT plus 2C Vx WX. All right, so we do the substitution. Before that, we factor out Vx WX, so 2A Vt Vx WT WX plus B Vt Vx plus WT Wx plus 2C here. Okay, so we have this one, and so we do the substitution by these two equations here. So we do the substitution. We find that this is equals to minus Vx, the x, and the b square minus 4ac divided by a. Okay. Okay. So, and you see that it also simplified. Okay. And which is non-zero for all points in V again. Okay, so that's if the semi-linear PDE in okay, so if our original semi-linear PD is hyperbolic V, it becomes very simplified. We double here, and we have A F tilde VW U tilde V U tilde W divided by Vx and Wx, okay, and the B square minus 4ac on the V prime by the characteristic coordinate transform. Okay, and so this form is 12.4.4. So the PDE in 12.4.4 is called the normal form of hyperbolic hyperbolic semi-linear PDE. Okay, so if the semi-linear PDE is hyperbolic, then we are able to use the characteristic coordinate transformation so that it becomes to a linear form, and which involve only the mixed single order partial derivatives. And the solution of this PDE become to be much more easier than the previous one. Okay, so this is called the normal form we have. Okay, if it is hyperbolic here. Okay, now because time limitation, so that I can get two other type, the parabolic and elliptic semi-linear PDE. We have, so let me write down the result, and I ask you to read my lecture notes. Okay, so if the semi-linear PDE in 2.4.1 is parabolic, okay, on V, i.e. the B square xt minus 4 axt cxt is equal to 0, or identical to 0 on V. Right, so this is 0 for every point xt on V. Okay, in this case. Then by characteristic coordinate transformation, okay, it becomes U tilde V equal to F, okay, F was VW U tilde V and divided by A on V. Okay, so you can simplify by assuming that A like equal So now we have for this simplified form. Okay, and this form is called a normal form. So this is called a normal the normal form of last case, if the semi-linear PDE in 12.4.1 is elliptic on V, i.e. B square xt minus 4a xt cxt is negative for all xt in V. Then, then I forgot, this is okay, so then by a coordinate transformation, related to complex characteristics, coordinate, right? Because that this is negative, so if we see here, we see that we have a complex equation. Okay, so now we have a complex characteristics. But for us, we will use real coordinate transformation. Okay, so we will have a coordinate transformation related to the complex characteristic coordinates. Then it becomes, okay, it becomes to here, U alpha plus U beta equal to 4a divided by 4ac minus b square times f tilde alpha beta u tilde u alpha tilde beta tilde alpha x square plus beta x square. Okay. So the coordinate transform is made by alpha beta, which is different from the VW, because now VW becomes complex characteristic curve. So which is not appropriate. So I have made some elaboration in my lecture notes different from the approach taken in the textbook. The textbook is weird for you, because in the textbook it uses the complex characteristics, right? So I think it's not appropriate. So I will give you the related coordinate transformations. And so you can see that the left-hand side is just a Laplacian. Okay, the left-hand side is a Laplacian of the U tilde. This is a Laplacian. And so that this form is called the Miller form of elliptic semi-linear PDE. Okay. So now you can see that we can simplify them in this way. Okay. Right. And so please please read the lecture notes for the detail. Okay. Right. So sorry, I have to stop here, and so that is for you to read. And so next week I will go to section number 6, okay, for the heat equation.